Welcome to the second part of our lecture, in which we'll continue discussing data link layer. In this part, we will discuss elementary data link protocols, a Utopian simplex protocol, a simplex stop and wait protocol, a simplex protocol for noisy channels. Before we start, we have some assumptions to make. First, the physical layer, the data link layer, and the network layer are three individual independent processes that communicate with each other through message passing. When machine A wants to transmit data to machine B, that would be a long stream of data on the top of a connection-oriented service which is reliable. Assumption 3, that machines do not crash because the protocols can handle data transmission issues but not crashing machines. The implementation can take different forms. One possible implementation is shown in the figure, where the physical layer and a part of the data link layer are implemented in pure hardware, that's to say a network interface card, and the rest of the data link layer is implemented in software in the form of device driver, and the network layer is implemented fully in software. The data link layer, the software part of it, and the network layer are both processes running in the operating system. Other possible implementations is for all three layers to be implemented in pure hardware, and that is known as network accelerator, or for all three layers to be implemented in pure software. The implementations varies from one place to another, from one application to another, from some time to another time. For sending a frame, a packet is accepted from the network layer, encapsulated in a frame, adding data link layer control data in a header and a trailer, and then transmitted over the physical channel. The process of receiving a frame, initially the receiver will just wait for the frame to be delivered. If the frame arrived, the hardware will compute the checksum. If the checksum is okay, then the control information in the header will be inspected. If everything is all right, the packet is extracted and passed to the network layer. We're not going to discuss any codes in the lecture, but it must be understood thoroughly. So you have to go back to the reference and study them. Our first protocol, the Utopian simplex protocol. It's called the Utopian protocol because it is making assumptions that are not realistic and can only happen in a perfect world. First is simplex because the data is transmitted in one direction only. It's utopian because the communication channel never damages or loses frames, because both transmitting and receiving network layers are always ready, because the processing time can be ignored, and because there is an infinite buffer space available. All these assumptions are unrealistic. That's why the protocol is utopian. In this protocol, the sender has infinite loop pumping data onto the communication link as fast as it can. The loop consists of 3 steps. Go fetch a packet from the network layer. The network layer is always ready. And construct an outbound frame by encapsulating the packet in the frame, adding control information and checksum. Then send the frame on its way. Only an information field is needed in this packet. No need for the checksum or the header because there is no data to be inserted. Hence, there is no errors and no need for flow control. Since we have said that the Utopian protocol is not realistic, we're trying to insert some real-world factors into our protocol here. Here, the traffic is still simplex, but the channel is still error-free. The only difference is that the receiver is not always ready, either because it's slower than the sender or because it has limited buffer. We can always add delay to protocol 1. So it will slow the sender down to match the receiver's speed. This can lead to low utilization for our bandwidth. It's better to provide the receiver with feedback to send it to the sender, permitting the sender to transmit the next frame. Protocol 2 here ensures that the sender cannot overwhelm the receiver with data. The receiver has to return an acknowledgement when it's ready, and only the frame will be sent if the acknowledgement was received. This is called stop and wait. And here we go, we added control flow. The implementation of the protocol looks like this. A sends data to B, B sends an acknowledgement telling A that it can send data again. A sends the next data. It waits until it gets an acknowledgement from B, then it sends the following data, and so forth. But things are not always this perfect. Issues. Our third protocol is a protocol for noisy channels. The traffic is still simplex, the communication channel is not error-free, and the receiver is not always ready. The possible solutions is that to add a timer to protocol 2, where the sender set a timer, waiting for the acknowledgement to reach the sender. If the acknowledgement did not reach the sender before the timer goes off, the sender then will retransmit the data. The problem here is if the acknowledgement was lost while the data has reached the receiver, the data will be duplicated and there will be duplicated packets delivered to the network layer, which compromise our basic rules. The other option is to add timer and frame numbering to protocol 2. Protocols where the sender waits for the positive acknowledgement from the receiver before proceeding in sending data are called PAR, positive acknowledgement with retransmission, or ARQ, automatic repeat request. ARQs adds error control also, because the receiver only acknowledges the data that reached intact, but the errorless data is not acknowledged or a negative acknowledgement is sent. The sender will set a timer waiting for the acknowledgement to come. If the acknowledgement did not come, the sender will retransmit the data. As we've said before, for correctness, the frames must be numbered. So the receiver will know if this is an original frame or a duplicate. For stop and wait protocols, like the one we are dealing with, the numbers 1 and 0 are quite sufficient, that's to say 1 bit. Here we can see a data error in transmission. The data reached from A reached B with an error. B sent a negative acknowledgement. A retransmits the data. B sends an acknowledgement, a positive acknowledgement, and A proceeds to next data. If the data did not reach B at all, B will send no acknowledgements. A timer will time out, and A then will retransmit the data, let the acknowledgement proceed to next data. The last option is the acknowledgement that did not reach A. The data has reached B safely, but the acknowledgement from B to A has been lost in the way. Here also, A will time out and resend the data. The data will be discarded at B, but after examining the number of the frame, and an acknowledgement will be sent. Then A can proceed to next data. Your assignment for reading this week is Computer Networks Andrew Stewart Tannenbaum, Chapter 3, Section 3.2. And your writing assignment is automatic repeat request. Thank you and see you next Tuesday, inshallah.